This line graph shows the P99 latency for a Go API service. The baseline sets perfectly flat at 10 milliseconds, but predictably spikes to 150. The anomaly is incredibly precise. The spike lasts exactly 30 seconds, triggering exactly every 15 minutes. This strict mechanical regularity proves it's not organic traffic. This flowchart tracks the initial investigation. The first suspect, garbage collection, but traces showed normal microsecond pauses, no 30-second locks. Distributed traces revealed the database was flat, just waiting on the network. Deployments and internal cron jobs were also clear. The internal application environment was completely clean. A service with highly optimized code and stable dependencies can still experience massive tail latency degradation. When the math inside the application checks out, standard profilers are looking in the wrong place. To diagnose the cause, the investigation must step outside the service's own observability metrics and look directly at the shared infrastructure node hosting the pod. This Kubernetes pod list shows 16 separate containers sharing the exact same physical hardware. One of those pods is a machine learning training batch job carrying a CPU limit of 14 cores, running on a 16-core machine. That specific batch job consumes 87.5% of the node's physical CPU capacity. It runs for exactly 30 seconds. It triggers exactly every 15 minutes. The schedule maps directly to the API's latency degradation. Logical container isolation in Kubernetes does not equal physical hardware isolation. When a resource-heavy workload is scheduled next to your code, that neighbor will violently degrade your performance. The mechanical theft of your latency happens deep inside the operating system layer. The Linux kernel uses the completely fair scheduler to allocate CPU time across containers, mapping out execution rights in strict 100 millisecond allocation windows. This diagram illustrates how CPU limits act as a hard cap. The kernel grants 200,000 microseconds per 100 millisecond period. If your container burns quota early, the kernel enforces a hard pause, suspending threads for 40 milliseconds, even if physical cores sit idle. Application profilers like pprof completely miss this event because they measure active CPU execution time, not suspended wall clock time. When the OS suspends a thread, the Go runtime receives no notification. To the profiler, the thread simply registers 0 CPU time. The tool lies by omission, hiding OS-level thread suspensions from the engineers trying to debug the resulting latency. The default behavior of application runtimes actively worsens this penalty. This graphic demonstrates the thread mismatch. The Bo runtime spins up 16 logical threads, ignoring the 2-core kernel quota. During a spike, 16 threads timeshare a quota built for 2. This thundering herd generates massive overhead, destroying 35% of throughput. Internal scheduling ignorance directly amplifies the noisy neighbor's impact. The runtime actively wastes the fractional CPU time the container is actually granted. Beyond kernel throttling, neighbors attack at the silicon layer. This CPU cache hierarchy shows fast private L1 cache. The 32 megabyte L3 cache is shared across every core on the socket. Main DRAM sits at the bottom, taking 100 nanoseconds per access. A standard Go API has a hot working set, connection pools, buffers, and compiled machine instructions that easily fit into the fast shared L3 cache during normal operation. But as this diagram shows, when the ML training job runs, it scans gigabytes of data. That massive sequential read floods the shared L3 cache, completely flushing the API's working set out to slow DRAM. This performance counter comparison quantifies the damage. During the ML batch, the API experiences a 22x increase in cache misses. To process a request, the API must fetch thousands of memory locations from DRAM, adding 60 microseconds per access. By simply touching shared memory, neighbors destroy your application's performance. They bypass CPU limits and logical isolation entirely. The final invisible bottleneck sits between the processor die and the physical DRAM sticks, the memory controller. This representation shows the ML jobs saturating the memory bus. A dual-channel server processor has roughly 85 gigabytes per second of bandwidth. A neighbor iterating through multi-gigabyte training batches can consume up to 90% of that capacity. When the bus is saturated, every memory-intensive operation your API attempts, specifically the sequential reads required for garbage collection, is forced to queue up behind the neighbor's massive data transfers. Extreme data transfers inflate latency across the entire node's architecture without ever triggering a standard CPU utilization alarm. Application metrics fail to diagnose contention. These schematics show the telemetry required to expose it: OS-level CPU.stat metrics to catch kernel throttling, and hardware-level performance counters to track cache evictions. This diagnosis playbook provides a strictly repeatable framework. By querying the cgroup file system for throttle events and running kubercontrol top during a spike window, engineers can directly correlate a specific neighbor's resource consumption with the exact timestamp of the latency anomaly. You can convert the total nanoseconds of throttled time into a per-request latency budget. This math directly validates the exact milliseconds added to your P99 graph. Moving from guessing to proving requires pulling telemetry from the exact physical layer where the contention occurs. The first software remediation is aligning your runtime with your quotas. Importing the Automax procs library forces Go to match its internal logical threads to the hard cgroup limit, instantly eliminating the thundering herd context switch overhead. This decision matrix details the infrastructure defenses. Low-cost fixes include applying pod anti-affinity rules to actively repel specific known batch jobs. The absolute complete solution is configuring dedicated node pools restricted exclusively to latency-sensitive workloads. This comparison demonstrates the result of physical isolation. Moving the service from a shared node to a dedicated API pool permanently flattens the P99 latency without a single code optimization. This table contrasts the illusion of local staging against the reality of production. Staging presents a sanitized, idle model with endless bandwidth. Production is a saturated, shared reality dictated by hardware constraints. Staging models application logic, but production tests hardware limits. Resilient engineering demands acknowledging the physical reality of the infrastructure and deploying the exact telemetry and node separation required to defend your code against the workloads running right beside it.